classic hot Jupiter. One of the most remarkable aspects of this exoplanet is its atmosphere. It was the first where scientists directly detected atmospheric components using spectroscopic observations during transits. Sodium was the first element identified, offering an initial glimpse into its composition. Later studies revealed the presence of water vapor, methane, and carbon dioxide, making it the first exoplanet with a multi-component atmospheric analysis. Another crucial discovery related to HD 209458b was its atmospheric escape. Observations from the Hubble Space Telescope revealed that the intense radiation from its star is stripping away the outer layers. This process, known as hydrodynamic escape, has created an enormous cloud of hydrogen trailing the planet, resembling a comet's tail. Due to this phenomenon, it was dubbed an evaporating planet. The estimated escape rate is about 10,000 tons of hydrogen per second, a significant loss, yet not enough to deplete its mass within billions of years. The planet has also played a major role in understanding cloud formation in extreme environments. High-altitude hazes and potential cloud structures inferred from its spectrum suggest the presence of scattering particles in its upper atmosphere. These findings have provided valuable insights into the physics and chemistry of exoplanetary atmospheres, helping refine models for other distant worlds. Another fascinating aspect of HD 209458b is its orbit. With an incredibly short orbital period of just 3.5 days, its proximity to the star generates strong tidal forces, likely causing it to be tidally locked. This means one hemisphere is in perpetual daylight while the other remains in eternal darkness. The extreme temperature gradient between the two sides results in violent atmospheric dynamics, including supersonic winds that redistribute heat. Beyond its scientific contributions, this exoplanet has played a key role in advancing observational techniques. Its discovery pushed the limits of spectroscopy, transit photometry, and atmospheric modeling. Initially confirmed via the radial velocity method, which detects a star's wobble due to an orbiting planet's gravity, it was later studied using both radial velocity and transit methods. This dual approach allowed for unprecedented precision in determining its mass, radius, and density, setting a new standard for exoplanet research. HD 209458b has also provided insights into planetary formation and migration. Theories suggest that hot Jupiters like this one did not form in their current orbits but migrated inward after forming farther from their stars. The exact mechanisms, whether interactions with the protoplanetary disk or gravitational influence, remain an active area. Studying this planet and similar ones helps refine models of pollution. Another intriguing challenge posed by this exoplanet is its unexpectedly large size. Its radius exceeds predictions based on standard planetary models, an issue known as the radius anomaly, which is common among hot Jupiters. Several explanations have been proposed, including additional heat sources where magnetic interactions between the planet and its extra energy. Continuation on HD 2098b provides valuable clues about these complex processes. Beyond its direct scientific impact, this planet has become a cultural and inspirational symbol in the search for extraterrestrial worlds. Its discovery and subsequent revelations about its atmosphere, orbit, and physical properties have captivated both scientists and the public. As a pioneering exoplanet represents how far humanity has come in exploring the universe beyond our solar system. In conclusion, HD 209458b remains a landmark discovery in modern astronomy. Its detection marked the beginning of a new era in exoplanetary science, and its detailed study has provided essential knowledge about planetary atmospheres, migration, and evolution. As a hot Jupiter gradually losing its atmosphere to its star, it serves as a natural laboratory for studying extreme planetary environments. The legacy of this exoplanet lies not just in what it has taught us about a single world, but in how it has paved the way for the exploration of countless others across the galaxy. HD 209458b is one of the most well-documented and fascinating exoplanets ever discovered. In the constellation Pegasus, this gas giant is located approximately 150 light-years from Earth. Its discovery in 1999 was groundbreaking, first exoplanet observed transiting its host star. The observation allowed scientists to study not only its orbit but also its physical and atmospheric characteristics in unprecedented detail, making it a cornerstone in the history of exoplanetary science. Often referred to as a pioneering hot Jupiter, HD 209458b has a mass roughly 220 times that of Earth, or about 0.7 times that of Jupiter. However, its radius is significantly larger, approximately 1.4 times that of Jupiter, classifying it as an inflated planet. This unexpectedly large size and low densitional models of planetary formation and structure. Researchers suspect that the intense stellar radiation from its host star contribute to this trait observed in many hot Jupiters. The planet follows an extremely tight orbit, circling its star at just 0.045 astronomical units (AU), and completing a full revolution 0.5. This close range exposes it to immense stellar radiation, heating its atmosphere to over 1000 Fahrenheit. Heat causes the atmosphere to expand and escape into space, earning it the classification of an evaporating planet. Observations from the Hubble Space Telescope have a cloud of hydrogen, of oxygen trailing behind the planet like a comet's tail. This large-scale atmospheric escape provides valuable insights into planetary atmospheres. The atmospheric composition of this exoplanet has been a major focus of scientific research. It was the first where atmospheric components were directly detected, setting a precedent for the study of exoplanetary atmospheres. Early observations identified sodium, but later studies revealed a more complex mix, including water vapor, methane, and carbon dioxide. Of water vapor was particularly significant, as it marked the first confirmed presence of water on a planet outside the solar system. This finding demonstrated the detailed atmospheric analysis of exoplanets, even those located light years away. Beyond Beyond its chemical composition, the planet's atmosphere exhibits extreme physical dynamics. It is believed to be tidally locked, with one hemisphere in constant daylight, while the other remains in perpetual darkness. This sharp contrast creates a dramatic temperature gradient, generating super that may reach speeds of up to 7,000 kilometers per hour, 4,350 miles per hour. These winds redistribute heat across, leading to turbulent and complex weather patterns. Observations have also suggested the presence of high altitudes, further complicating its atmospheric boundary of HD 209458b has special insights into planetary migration. Current models suggest that hot Jupiters like this one did present orbits but instead migrated inward after forming farther from their stars. The mechanisms responsible for this migration, with a protoplanetary disk or gravitational influences from other celestial bodies, remain an active area of research. The extreme proximity of this exoplanet to its star challenges existing theories and continues to prompt new investigations into the forces shaping planetary systems. Another enigmatic aspect of this world is its unexpectedly large radius. Standard planetary models struggle to explain this inflation exceeds expectation mass and temperature. Possible explanations include tidal heating, where gravitational interactions with the host star generate internal heat, or ohmic dissipation, a process in which the planet's magnetic field interacts with ionized gases in its atmosphere, converting kinetic energy into precise mechanism. This inflation remains ongoing research. This exoplanet has also played a key role in advancing astronomical observational techniques. Its discovery and subsequent characterization relied on a combination of the radial velocity transit photometry. The radial velocity method detects the gravitational wobble of a star caused by an orbiting planet, while the transit method measures the dip in a star's brightness as is in front of it. These techniques provided extensive details about the planet's mass, radius, orbital period, and atmospheric properties. This dual method approach has since become a standard in exoplanetary research, facilitating the discovery and analysis of thousands of distant worlds. The significance of HD 209458b its own unique characteristics. Discovery and extensive study have paved the way for further exploration of exoplanets in spatial tools. For example, the James Webb Space Telescope is expected to build upon its legacy by offering even more detailed observations of exoplanetary atmospheres. The techniques used to analyze this gas influence coming project European Spiral mission, which aims to examine the atmospheres of hundreds of exoplanets. In conclusion, HD 2094, often referred to as the evaporating planet, the roaster world, or the inflated gas sphere, remains a landmark in the study of exoplanets. Its discovery marked the beginning of a new era, while its detailed characterization has provided unparalleled insights into planetary atmospheres, migration, and evolution. As one of the most exoplanets, it can serve as a natural laboratory for physics and chemistry of extreme planetary environments. Its legacy is not only in what it has revealed about its own unique properties, but also in its role as a catalyst for the exploration of countless other worlds across the galaxy. HD 209458b continues to be a cornerstone of exoplanetary science, inspiring new generations of research into planetary systems beyond our own. Its atmospheric properties, orbital mechanics, and contributions to advancing observational techniques provide a near-endless array of opportunities. Science exoplanet as a proving growing methods that characterize distant worlds only in terms of their fundamental parameters, but also their complex behaviors and interactions with their host stars. One of the most remarkable aspects of this boiling exoplanet is its evaporating atmosphere. The hydrodynamic escape of hydrogen, oxygen, and carbon detected from the planet provided the first direct evidence of large-scale atmospheric loss on an exoplanet. This phenomenon has significant implications for understanding the long-term evolution of atmospheres, particularly for those in close proximity to stars. Atmospheric escape can strip smaller planets of their gaseous envelopes entirely, potentially leaving behind barren rocky worlds. Studying this extreme case allows scientists to model the process under the most intense conditions, offering valuable insights applicable to a broad range of planetary systems. Beyond atmospheric loss, this exoplanet serves as a fascinating case study for tidal locking dynamics. Likely locked in a synchronous orbit, one hemisphere remains in constant daylight while the other is permanently shrouded in darkness. This configuration results in extreme thermal contrasts, with the day side reaching blistering temperatures while the night side remains significantly cooler. The redistribution of heat between these two hemispheres is aided by supersonic winds driven by intense stellar radiation. These high-speed currents transport energy across the planet, influencing atmospheric actions. Researchers gain valuable insights into atmospheric behavior and tidal locking conditions, which is also relevant to rocky exoplanets' inhabitable zones. The inflated size of HD HD2058b remains another puzzle. Its radius exceeds theoretical for a planet of its mass, leading to ongoing debates about the mechanisms responsible for this anomaly. Tidal heating, caused by gravitational interactions with its star, creates sufficient internal heat to expand its gaseous envelope. Another possible explanation is ohmic dissipation, where interactions between the planet's magnetic field and ionized atmospheric particles produce additional heating. These processes, while still theoretical, highlight the complexity of physics and the need observations to refine our understanding. This exoplanet has significantly advanced our knowledge of the detection of sodium, water vapor, methane, and carbon dioxide in it marked a turning point in exoplanet research. Discoveries, made possible through spectroscopy, have allowed scientists to analyze the starlight passing through the planet's atmosphere during transit. Studying absorption features in the spectrum, researchers can identify specific molecules and estimate their abundances. This breakthrough not only provided a clearer picture of HD 209458b's atmospheric composition but also laid the groundwork for studying atmospheres on smaller and potentially habitable exoplanets. Another key contribution of this planet is its role in understanding planet-star interactions. Intense radiation and stellar winds from its host star play a crucial role in driving atmospheric escape. These forces alter its magnetosphere, which helps shield the planet from high-energy particles. Examining its magnetic environment provides valuable insights into how planets in extreme conditions protect themselves from stellar radiation. Such studies have broader implications for assessing the habitability of planets orbiting active or young stars. HD 2094 has also deepened our understanding of planetary migration. Hot Jupiters like this one are believed to form much farther from their stars in colder regions before migrating inward. The exact mechanism behind this movement, whether through the protoplanetary disk, gravitational perturbations from other celestial bodies, or a combination of factors, remains a topic of active research. The orbital properties of this gas giant, combined with its atmospheric and physical characteristics, provide critical data for refining these theories. Additionally, the presence of high-altitude hazes and clouds in its atmosphere has enhanced our understanding of aerosols in exoplanetary environments. These hazes scatter light and obscure certain spectral features, complicating the detection of atmospheric molecules. Study effects have been able to develop the accuracy of atmospheric retrievals for other exoplanets. This research is crucial for upcoming missions aiming to characterize the atmospheres of Earth-like planets, where clouds and hazes may similarly impact observations. This giant close-in planet also serves as a natural laboratory for studying extreme stellar irradiation. The intense heat it experiences profoundly impacts its atmospheric chemistry, potentially triggering photochemical reactions that produce exotic molecules. These are of great interest to researchers studying planetary chemistry across a range of conditions, including those found on temperate worlds. Finally, the cultural and scientific legacy of HD 20945 cannot be overstated. As the first transiting exoplanet ever discovered, it has inspired countless and played a pivotal role in shaping modern exoplanet. Its detection marked the dawn of an era where characterization of distant planets became possible. The techniques refined through its study have since been applied to thousands of other exoplanets, understanding of the diverse planetary systems within our galaxy. In summary, HD 20945b, often referred to as the boiling gas giant, the evaporating planet, or the roaster world, remains a fundamental target in exoplanetary research. Its unique characteristics, from atmospheric escape to extreme weather patterns and inflated size, have provided unparalleled insights into planetary physics, chemistry, and evolution. As a triplanet, it continues to drive new discoveries and innovations, cementing its legacy as a key stepping stone in our quest to understand the cosmos. HD 20945, known as the evaporating planet, or the inflated giant, is far more than a scientific curiosity. It stands as a beacon, illuminating the vast, complex, and untamed world of exoplanets. While much of its physical nature has been studied, lingering mysteries and tantalizing possibilities continue to intrigue scientists. The deeper we probe into its secrets, the more it reshapes our understanding of planetary science, reminding us of how much more remains to be uncovered. One of the most fascinating aspects of is its role as the prototype for studying atmospheric escape. When the Hubble Space Telescope first detected hydrogen being stripped from its upper atmosphere, forming a massive comet-like tail, it opened an entirely new field of research. But this process isn't just about mass loss, it's about the planet is undergoing a slow yet steady evolution, sculpted by its star's intense ultraviolet. This erosion raises profound questions. Is it in a transient phase, destined to be entirely different in millions of years? Could it eventually shrink into a rocky core, resembling a super-Earth or a mini-Neptune of its gaseous envelope? Even more captivating is the planetary alchemist. Under the relentless glare of its star, molecules in the atmosphere are broken apart, triggering complex. The interplay between chemistry may produce exotic compounds that cannot form under any other. Could its atmosphere harbor unexpected molecular treasures, rare metallic vapors or charged that challenge existing chemical models? Some researchers even speculate extreme environments might offer clues about how complex molecules form in space, potentially shedding light on the origins of life. Beyond its atmospheric escape, HD 2058b is an extraordinary case study in mythology. While Earth's climate by relatively mild interactions between the sun, ocean, atmosphere, conditions here are defined by extremes. The scorching heat of its day, chill of its night, planetary furnace, supersonic winds exceeding 7,000 kilometers per hour, 4,350 miles per hour. But what's really those winds? Could they be mixing atmospheric layers in ways that defy our models? Could they transport elements or compounds in patterns that mirror, but vastly amplify, the jet streams and ocean currents of Earth? Perhaps one of the most provocative questions concerns its long-term. If the planet's atmosphere continues to erode of years, what will remain? Current estimates suggest around 10,000 tons of hydrogen every second. While this rate is insignificant relative to its total mass, it could one day reveal a hidden core. What lies beneath the thick atmosphere? Core of rock and metal, or something more exotic? Could this once blazing gas giant eventually become a barren, rocky artifact of its tumultuous history? HD 209458 challenges traditional planetary classifications. In our solar system, we fall into rocky worlds or gas giants, but this exoplanet doesn't fit so easily. Its diffuse, oversized atmosphere of a star's coronal, could it represent an intermediate between planets and failed stars like us? Challenge us to read it when considering its inflated size. Traditional models of planetary formation and structure struggle to explain why its radius is significantly larger. Could unknown work here? Some theories suggest that tidal forces from its generate immense internal heat, expanding the planet. Others propose interactions with charged atmospheric particles create additional energy, keeping it puffed up. What if these theories only scratch? This planet hold the key to uncovering new physics interior? Then there is the enigma of its clouds. Observations suggest high-altitude hazes composed of exotic materials like silicates or metals. These particles may scatter light in unexpected ways, creating spectral signatures that are these forming in dissipates violent winds? Or are they a permanent feature, shielding deeper layers from observation? Their presence may be both a barrier and a window into the planet's secrets. Beyond its scientific importance, HD 209458b holds cultural significance as well. As the first transiting exoplanet ever discovered, it opened the door to a universe. Its detection revolutionized astronomy, the way for missions like Kepler and the James Webb Space Telescope, which now push of exoplanets. This world story is not just one science, it is one of humanity's unrelenting curiosity and drive to explore the unknown. There is also the tantalizing possibility that this gas giant is not alone. While no additional confirmed in its cylinder often hints at a more complex planetary arrangement. Could Saki worlds be orbiting farther out, hidden from current detection methods? Has the migration atmospheric loss of HD 209458b influenced its hypothetical shaping their positions? The possibility of an unseen planetary family only adds to its allure. In many ways, this exoplanet is not just a world. It's a puzzle, a paradox, and a promise of future discoveries. It has already revolutionized our understanding of distant planets, yet it continues to pose new return. Every observation, every model, and every theory brings us closer to unraveling its mysteries, yet new enigmas always emerge. HD 209458b stands as a testament to the infinite complexity of the cosmos, a world that challenges our assumptions and fuels our imagination. It is a reminder that the universe is far more dynamic, diverse, and surprising than we ever dared to dream. And perhaps, hidden in its fiery winds and evaporating atmosphere, lies the next great revelation in our quest to understand the stars. HD 209458b, often hailed as the trailblazer of exoplanets, is more than a scientific curiosity, it is a gateway to understanding the extremes of planetary science. Much has been revealed about this enigmatic world, each new to unveil yet another layer of complexity, keeping astronomers captivated. The very essence of Osiris lies in its dynamic nature, a planet in transition, constantly reshaped by the intense forces at play within its star system. This ongoing transformation provides a natural laboratory for exploring planetary evolution, atmospheric physics, and even the boundaries of what defines a planet. One of its most mesmerizing features is the vast, comet-like tail of hydrogen trailing behind it, a direct consequence of atmospheric escape. Observations of this allowed astronomers to quantify the rate, providing unprecedented interstellar radiation interacts with planetary atmospheres. However, the loss of hydrogen is only part of a larger story. Recent studies suggest that heavier elements, such as oxygen and carbon, are also escaping, albeit at lower rates. All raises a loss will be revealed beneath. Atmospheric loss is not just an interesting feature, it could redefine the planet's future. Could HD 209458b eventually shed its entire atmosphere, leaving behind a dense? If so, what would this exposed remnant look like? Would it resemble the scorched rocky planets observed in other systems, or something entirely? Some theorists speculate that stripped-down remnants of gas giants might evolve into certain types of super-Earths, bridging the gap between terrestrial and gaseous planets. If Osiris is indeed undergoing such a transformation, it could offer a rare glimpse into a transitional phase of planetary development. Even as its atmosphere thins, the interactions between the planet and its star continue to detail environments. The closes it to intense stellar generating a unique interplay of its magnetic field and charged particles from the. Some models suggest that Osiris might generate auroras far more powerful than those seen on Earth or Jupiter. These massive, planet-wide auroras could glow faintly in exotic colors, fueled by ionized gases in the upper atmosphere. While we cannot yet directly observe these phenomena, they hint at the complex electromagnetic environment surrounding this distant world. The planet's inflated size remains an enduring mystery. Despite decades of study, scientists are to determine why critical predictions radii. One leading theory suggests complexing forces in its star generate heat deep within, causing atmospheric expansion. Another hypothesis points to ohmic dissipation reactions between magnetic fields and ionized gases convert energy into stasis not only deepens our knowledge but valuable insights into hot Jupiters. Osiris's atmosphere is another source of intrigue, particularly chemical the presence of sodium, methane, oxides, whatward. Relentless from its star-like reactions like compounds, such as metal oxides, molecules may in trace amounts, but they could provide crucial clues about the interplay between radiation in extreme environments. The Prelude Haze atmospheric studies. Aerosols obscure spectral features at different layers. Made of? Could they contain silicate particles, metallic compounds, or even unidentified materials that are another puzzle? Tidal locking creates a stark temperature contrast between the blistering and the cooler night side, resulting in patterns. Supersonic winds sweep across the atmosphere to support heat unevenly, forming shifting climate models. Could these dynamic processes create temporary regions in otherwise chaotic atmosphere? If so, what unexpected chemical interactions might occur in these transient zones? Perhaps most intriguingly, some D2458b still defy explanation. Despite advancements in exoplanetary science, observations of Osiris remain inconsistent with existing models. For example, the observed rate is higher than predicted, suggesting that additional factors, such as stronger than expected interactions or previously unknown atmospheric mechanisms, could be amplifying the Alternatively, entirely new physical processes may be at work, waiting to be discovered. The influence of this exoplanet extends far beyond its own system. As the first transiting revolutionized astronomy and paved the way for nearly every major exoplanetary mission since, instruments like Space Telescope and the European Spatial Mission are direct beneficiaries of the techniques in its study. These missions build on by spheres of smaller, cooler planets, including potentially habitable worlds. The 2098b has brought us closer to answering one of humanity's most profound questions: are we alone in the universe? Yet, even as we look to the future, Osiris reminds us of the importance of revisiting what we think we know. Each new observation has the potential to overturn previous assumptions, revealing deeper complexity. High-resolution have already detected in atmospheric suggests chemistry may evolve over time. Could these changes be driven by seasonal variations, or are they solely the result of external influences, such as fluctuation activity? This planetolic weight. It is not just an object of study but a story, a narrative of survival, and the relentless interplay of forces that planets are entities but dynamic, constantly evolving in response to their environments. Osiris challenges beyond the familiar, to imagine systems that operate under entirely different rules, and to embrace the infinite diversity of the universe. As telescopes grow more powerful and observational techniques more refined, of HD 2058b unfold, with its boiling, violent winds in nature, it will remain a focal point for scientific exploration, a world that will fit neatly into existing categories of advance of the cosmos. It stands as a beacon of discovering us exists deeper. HD 209458b, often Osiris, continues astronomers with its defiance of convention and the mysteries it fully reveal. Blazing Titan, locked in an eternal embrace, is more than an object, it is a cosmic enigma. Its structure and evolution challenge fundamentalists, leaving us to wonder how much more has to teach us and what answers it might questions we haven't yet thought. One of its most striking features is its presence. While it is designed for a world that is continuously a sphere, it is in constant conflict with its environment. Every second, thousands of tons of hydrogen escape into space, loss that should, in theory, spell its demise. Yet, despite this ongoing depletion, the planet endures. Could an unknown stabilizing factor be at play, or is this merely age in its transformation? The conditions beyond heated to temperatures high enough to vaporize rock side experience winds that eat into darkness. Pressures reach such intensities that even hydrogen, typically the lightest and most forms dense, massive layers. Could these deep regions harbor exotic states of matter, such as metallic hydrogen, conducting heat and electricity in ways unimaginable on Earth? This planet may serve as a laboratory for entirely new realms of planetary physics. Its atmosphere, constantly bombarded by ultraviolet and X-ray radiation, undergoes violent transformations, unpredictable chemical reactions. This relentless energy assault may be forging rare or even unknown compounds, in an environment unlike any in the solar system. The search for these exotic molecules pushes the limits of spectroscopic technology, as scientists attempt to extract faint chemical signatures hidden within observational data. Beyond its internal turmoil, the relationship with its parent star adds another complexity. Sphere forces create oscillations detectable from light years away. Some theorists suggest that extreme tidal interactions could even influence the star's outer layers, leading to this would mean the planet is not merely a passive recipient of its star's influence, but an active participant in shaping the system's dynamics. The presence of a magnetosphere, if confirmed, could be another crucial factor in understanding its long-term survival. A strong wind might deflect a portion of the stellar wind, slowing atmospheric escape. But this protective barrier could come with its own consequences. Interactions between magnetic fields, charged particles, and ionized gases might generate immense currents and even planetary-scale lightning storms. Though invisible from Earth, such phenomena could turn the planet into a world of light, where flashes of electricity illuminate its turbulent skies. For all its chaos, there may be underlying patterns at work. Infrared observations indicate that heat distribution across isn't as random as previously thought. Hot spots appear slightly off-center from expected locations, hinting at high-speed wind energy in complex and unexpected. The movement of these zones over time suggests that the atmosphere functions like a vast, dynamic influenced by forces still not fully understood. Are these shifts driven by internal atmospheric dynamics, or do they respond to changes in the star's activity? Its current orbit raises further questions. A planet this large, this close to its star, likely did not form in place. Instead, it must have migrated inward from a more distant, stable region. What caused this journey? Did it once have a planetary sibling that was ejected from the system, or was it drawn inward through interactions with the protoplanetary disk? If this migration, as some models suggest, realized other planets in the system, leaving behind a history of gravitational upheaval, this be the lone survivor of such an event, bearing scars of a violent past. Looking ahead, this planet may glimpse into the future of other worlds. As stars age and swell into red giants, they unleash even greater radiation upon their planetary systems. For a world already enduring extreme conditions, this transformation could be catastrophic. Will it eventually be stripped entirely of its atmosphere, leaving behind a barren core adrift in space? Or will it adapt, clinging to some remnant of its original form in ways we cannot yet predict? make a model for studying planetary evolution, not just within its own system but even of temporary spheric stability, fleeting region temperature formation of unusual compounds. These transient pockets evolve under extreme conditions, analogues to the early rocky planets like Earth. Studying this hot Jupiter could unexpectedly help us better understand our own planet's past. Finally, there is the question of whether this world is truly an outlier. Thousands of exoplanets have been discovered since its transit was first observed, yet it remains among the most compelling. Is it a rare anomaly, or does it represent an entire class of planets so extreme that they push the boundaries of current classification? If the latter, what does this reveal about the chaotic, unpredictable nature of planetary? The more we learn, the clearer the universe does not adhere to rigid instead produces by an intricate interplay of forces we are to grasp. The story of HD 2058b is far from over. Each new observation, theoretical breakthrough, and technological advancement adds to its narrative is a world of contradictions and mysteries fuses to conform to and continuously challenges the limits of our understanding. As our explore the cosmos advances, it serves as a reminder most inhospitable corners of the universe, discovery thrives. It is a proof that the person knows no bounds, and a testament to the bounty of the cosmos. Whatever the future world remains is to be ignored. As long as we seek to understand, it will continue to listen. The saga of HD 2098b that grows and fascinates. This has become a cornerstone of science, a world that defies easy classification and challenges our understanding of the physical laws governing planets. After decades of oddity, it continues to lead the cast of the heart of battle and its host atmosphere steadily fight back, gash despite the violet radiation, going to an extreme almost otherworldly. Yet, this makes it a scientific treasure trove. By study of atmospheric erosion, scientists gain insights into exoplanets' evolution but also of countless other worlds orbiting close to their stars. One particularly intriguing atmospheric loss is escape of heavier elements oxygen and carbon. While hydrogen is light enough to be carried away, the elements suggest powerful force atmosphere. Could magnets or mercury understanding these processes are crucial clues from evolution this planet or hot smaller rock. The atmosphere, a constantly shifting and physical chaos, reveals surprises. Among the most significant is the presence of water vapor, detected through detailed spectroscopic analysis. This finding was groundbreaking at the time. Water may be just the extreme heat and radiation could be driving the formation of more complex molecules, carbon-based compound unfamiliar forms. Could this environment harbor traces of prebiotics, or does it intend any such possibility? The question for research, pushing to refine their models of atmospheric. The planet's weather pattern are of intrigue. Winds here are unlike anything seen on Earth, reaching speeds that could encircle the planet. These violent rise from the stark temperature between the scorching day side and the relatively cooler night side. Models suggest that atmospheric dynamics may be even more chaotic than previously thought, with jet streams, vortices, and localized storms forming and dissipating in rapid rotation and intense stellar heating. If we could observe these phenomena directly, towering clouds of metallic vapor, leading flows of ionite by electrons, the idea stretches the imagination. Beneath the turbulent atmosphere lies a region beyond direct observation to understanding the planet's origins. Similar to dense mix of rock and metallic hydrogen, or something entirely different, shaped by the conditions of its migration and exposure to intense radiation. Some theorists speculate ionic water state of molecules exist as fluid, conducting electricity with astonishing. If such an exotic exists, it could influence the planet's magnetic field and internal structure. Of magnetism, the presence of a magnetosphere remains a compelling mystery. While measured directly, magnetic field locations for atmospheric escapes with the star. If present, it could act as reducing mass losses while simultaneously generating sporas. Planet-wide light shows far more intense than anything seen on Earth. Would these auroral unions on more exotic hues, dictated by the history of this alien world? It extends beyond its atmosphere and internal very existence in its current orbit. It is unlikely that the form so close to its star must have migrated inward from a more distant, cooler system. What triggered the gravitational interactions in it? Or was it drawn inward through a slow dance with the protoplanetary disk? If it's migrative as some models suggest, it may have distinct, potentially history of own survivor and scars of a possible planet remains an open. While no other confirmed orbiting its star of a hot Jupiter at a planetary color, rocky planet from our detection method, or is there evidence history could is a solitary with a larger family? Exoplanet also to think about the future, specific discovery-driven observations like Space telescopes is standing, but it also every yearly a doorway to new questions. Lies beyond planet in the years of exoplanets. What other world action will they hold? In many D2 just a planet symbol of the ultimate to the boundless creativity of the cosmos. It demonstrates the harshest, most extreme environments, there is beauty, complexity, and the potential. Let's continue to study this world and other expanding our knowledge, uncovering about our own place in the universe and the influence that lies. Each 9400 B stands as a cosmos that appears to defy its own survival while simultaneously thriving in the extreme conditions imposed by it. Scientists explore this enigmatic world itself as a unanswered question possibility far beyond. Every exoplanet opens mysteries, ensuring that it will release a planetary generation. Most comes of this world is the boundaries of either too hot, its expectations, perceptible odds, could this that are having questions that in way early static chemistry abilities what is in its environment. The question of it remains in planetary that this roaster life in a month of its star city accepted, but the specifics of its journey remain elusive. What forces guide current orbit? Gravitational interplanet long since ejected or consumed? Did it stabilize other celestial bodies, scattering smaller planets to interstellar space? Was its slow spiral through the planet single jetting light on sculptums through its atmosphere is not merely escaping, it is a tail trail most visible slate that carbon lost lower. This raises this loss over information recognized. Do the processes at work in its atmosphere mirror potential atmosphere other worlds, including Earth, under extreme conditions? The scorching environment is equally fascinating. Subjected to emission, constant in way existing models and power for the form includers and cis. Could in its atmosphere natural analogs on sting only under conditions? Studying them could provide just into UV and materials research. Though across this fought another layer of drama, super-driven considering the relative chaotic environment. Models suggest jets through the planet, transporting heat in unpins. These two unseen in the solar system. Empirical reaction of the shear finds this exoplanet. Its roiling atmosphere lies a realm beyond direct yet central to understand. What resides within? Is it a rocky center like that of does it harbor hot Jupiters? Some research a core ionic ways of adlatin ion, Atanius lit and soft. Such an exotic only redefining of planets into the presence of an adds intrigue. If a strong exists sphere for slow law, protection would between the magnetic part the stellar wind could generate immense electrical currents, lighting up the planet are more powerful than anything seen in our solar. These glowing arc if be the most testament to the ongoing between the planet and its star, a battle pillars and light-brilliant skies. Beyond its current state, this planet may into the future of planetary evolution. While its extreme condition hospitable, the processes are not unique. Many stars will move into red, engulfing their inner planets in radiation and stellar winds. Could this world of what might happen to Earth as their stars age and could escape wide clues might change conditions? Billions of these questions elevate its significance from a singular curiosity to a of the pending planetary evolution on a cosmic scale. This world also inspires other exoplanets, and the techniques it of identifying thousands now await detailed. With advanced instruments open such scientists to explore polar, cooler, and potential. Yet in shifts to the candidates of extreme worlds remains invaluable. The searing heat, chaotic winds, and evaporative HD 205 estimates to the sheer diversity system and the cosmos. This plan in every refined model, more of its secrets are, yet new questions rise. It is a world of extremes, a living experimentary physics, chemistry, and evolution. As exploration continues, this remains a symbol of our quest to understand the cosmos, that even the most hostile environments can hold beauty, promise of discovery. It challenges bigger, to put our knowledge, face the infinities that await us among the 258b, or Osiris, piece of cosmic extremity, dances precariously close of destruction, yet throttles way. Its origin and enigmatic, one of the most studied and theorized planets in the universe. Yet, as much as we've uncovered, it feels as though we're gazing through a fog of truths that seem reach. It is not mere, it is quite a universe itself, humanity's brightest minds, HD 205 known as continued scientists, feature, and evaporate, visibly trails behind it like a culture. A vast comet-like tail, undeniable relentless radiation from its host star stripping away its outer layers. But this injection of heavier oxygen, and even escaping the planet's gravitons at an even more commanding transformation. How long has this process been reshaping the planet? Harbored a much denser atmosphere, or perhaps even moons, now lost to the slow yet unyielding forces of stellar trajectory beyond questions. Current suggest that while it will take to be stripped entirely of effect will inevitably reshape it. A brief moment of a dying world, rocking the scars of its past, or completely, leaving it contributed to interstellar space. The chemistry within its turbulence, another layer of methane, carbon dioxide and sodium, but scratched the surface of a much exotic compound. Its extreme condensation bubbles, their fragments into new chemical species that may be unknown in more temperate environments. Could these high-energy reactions serve as precursors to the complex chemistry seen in coastal? Some researchers speculate that, despite its inhospitable nature, the world may provide insight building blocks of chemistry itself. History, lightning and solar radiation synthesizing organic molecules to life. Osiris's upper atmosphere is more extra, allowing study how matter behaves under some of the most intense conditions. Life could understanding how molecular structure evolve under such duress could reveal new pathways for chemistry across the volatile atmosphere emerges. Osiris's blow 1.4 times Jupiter rotations give his counter-intentional models range from to its cosmic dissipation, where its interacts with atmosphere, generating internal heat. Explanation. Some researchers the intense pressures and temperatures within to exotic material metallic hydrogenic water behave in ways on Earth. If these exotic could shape everything from the planet's heat magnetic field, infinitum stability and evolution. Unlock to transform our understanding of gas including Jupiter. Field does exist, its effects would be magnetosphere could provide a degree of shielding, deflecting some of the charged particles from the stellar wind and slowing atmospheric escape. However, such a force would also have unintended. The interactions between the magnetic field, ionized gases, and stellar radiation could generate massive electrical currents, potentially creating planet-wide auroras or plasma storms of unprecedented scale. If such auroras exist, they would be unlike anything seen on Earth. Rather than soft, flickering waves of green and blue, these would be violent arcs of energy, stretching across the entire night sky, even from interstellar distances. The unique chemistry of the atmosphere could give rise to entirely new colors, fiery reds, deep purples, or even metallic hues. These displays, if observed, would offer a dramatic visual representation of the constant between the planet and its star. Osiris's current proximity to its host star suggests a dramatic past. Theories of planetary formation indicate that gas giants form much farther out, where cooler conditions allow volatile compounds to condense. For it to have reached its perilous orbit, migrated inward, a journey that would have been anything but peaceful. Did it interact with other planets, ejecting them from the system or even consuming them? Could it have destabilized an entire planetary neighborhood in its relentless inward drift? The scars of this journey may still be imprinted in its composition and structure. Its core could hold remnants of the materials it encountered, while its atmosphere might carry traces of other celestial bodies it disturbed or absorbed. Could it have once been part of a grander planetary system, now left fragmentational influence? If so, it stands as both a survivor and a catalyst of destruction, a world that has endured the chaos it may have helped unleash. Looking forward, the fate of this planet remains an open question. Its atmosphere will continue to erode, and its interactions with its star will intensify as the star itself evolves. Will it shrink into a dense, lifeless core, a shadow of its former self? Or could it be entirely consumed by its sun, an act of fiery dissolution into the stellar inferno? This relentless transformation serves as a stark reminder of the impermanence of even the most massive celestial bodies. Beyond its own destiny, Osiris offers a glimpse into the potential future of planetary systems like our own. As the Sun ages, it will expand into a red giant, likely engulfing Mercury, Venus, and perhaps even Earth. The processes unfolding on this distant exoplanet may foreshadow the fate of worlds much closer to home. It's a rare opportunity to study, in real time, the mechanisms that shape planetary evolution on a cosmic scale. More than just a scientific curiosity, Osiris represents the power of human curiosity and ingenuity. Its discovery helped pave the way for modern exoplanetary research, and its study continues to push the boundaries of what we understand about planetary atmospheres, chemistry, and migration. It serves as a reminder that the universe is far stranger than we can yet comprehend, its mysteries stretching beyond the limits of imagination. And in that strangeness lies the promise of discovery, the thrill of the unknown, and the relentless pursuit of understanding the worlds beyond our own. HD 209458b stands at the edge of what we know about planets, constantly inviting us to push further into the unknown. It is a world of contradictions, caught in a cycle of relentless destruction yet displaying extraordinary endurance, a chaotic battlefield of forces that somehow maintains an intricate cosmic balance. More than just a scientific curiosity, this distant exoplanet challenges not only our understanding of planetary science but also our perception of what is possible in the universe. Its ongoing transformation is a testament to nature's creativity and the unpredictable forces shaping planets on a galactic scale. As its atmosphere steadily escapes, new questions emerge. What happens to the lost material? While hydrogen disperses into interstellar space, heavier elements such as oxygen and carbon may linger, forming transient clouds or interacting with stellar winds to create unexpected structures. Could this world be leaving an invisible trail, a legacy of its atmospheric unraveling etched across its system? By studying this escaping gas, scientists can uncover secrets about its chemical history. The ratio of hydrogen to heavier elements in the planetary tail may reflect its formation. Is this giant originally enveloped in a more complex atmosphere, or has it always been predominantly hydrogen and helium? Reconstructing its past through its evaporative footprint could provide key insights into how similar planets evolve. The extreme heat of its day side, soaring beyond 1 Celsius 1800 degrees Fahrenheit, drives a furnace-like reaction, shaping atmospheric behavior in ways yet to be fully understood. Intense stellar radiation not only heats but ionizes the gas, creating an electrically charged environment where exotic weather patterns may unfold. Metallic clouds could form and dissipate in cycles, while supersonic winds sweep ionized currents across the planet at unimaginable speeds. Some models suggest that this turbulent system is like a planetary heat engine, redistributing energy unpredictably. Certain atmospheric layers are temporary barriers, forcing heat to escape in bursts and generating shockwaves that ripple through the skies. These violent disturbances could explain some of the spectral variations observed, hinting at a dynamic and volatile climate. Beneath the upper atmosphere, an even greater mystery lies hidden. The core is more than just a structural foundation, it is a time capsule preserving the conditions under which this planet formed billions of years ago. Enriched with heavy elements, scarred by a violent migration, or does its composition suggest a more gradual evolution? Some scientists speculate that tidal interactions with its star may have partially melted the core, contributing to its anomalously inflated size. If true, this would be unusual in the known universe. Beyond its atmosphere and core, this world may produce breathtaking displays of light. Charged particles from escaping gases, interacting with stellar radiation, could generate auroras far beyond anything seen in our solar system. These luminous arcs might stretch across the entire night side, bathing the planet in a perpetual glow visible from distant star systems. Its evaporating atmosphere may also shimmer with ionized gases, forming a ghostly halo around the planet. Combined with an immense hydrogen tail, these glowing remnants could make this gas giant one of the most visually spectacular objects in its system, if only we could see it up close. Yet this is not just an object of study, it is a planet in the midst of profound change, and its impact may extend far beyond itself. As mass is lost, the escaping material could seed nearby space with elements that may one day contribute to the formation of new stars and planets. In this way, it is not merely a dying world but a participant in the cosmic cycle of creation and destruction. Its story also forces us to consider the broader fate of planetary systems. Could other hot Jupiters represent a fleeting but common phase in planetary evolution? If so, how many similar worlds are undergoing comparable transformation, atmospheres dissolving unnoticed in distant star systems? The study of this extreme environment compels us to look beyond a single planet and contemplate the unseen dramas playing out across the universe. Perhaps the most profound lesson it offers is not about its atmosphere, core, or migration but about perspective. What does this distant world teach us about our place in the cosmos? It exists in conditions wholly alien to Earth, yet its study reveals universal principles, gravity, energy, motion, and chemistry, that apply everywhere. In this way, it is both familiar and alien, a reminder that while planets may differ in their extremes, they are all governed by the same fundamental forces. As we refine our methods of planetary observation, this world remains a beacon, a symbol of the challenges and rewards of venturing beyond our solar system. It reminds us that even in the harshest, most unforgiving environments, there is complexity, beauty, and a story waiting to be told. It pushes us to imagine what might lie beyond, to dream of distant worlds, and to embrace the boundless possibilities of the universe. Its story is far from complete. With each new observation, refined model, and technological breakthrough, we inch closer to understanding the full nature of this extraordinary planet. Yet, for every answer we uncover, new mysteries arise, ensuring that it will continue to captivate us for generations to come. More than just an exoplanet, it reflects the fundamental processes shaping the cosmos: creation, destruction, transformation, and renewal. It embodies a paradox, a planet losing itself to its star, yet persisting, a world operating at the extremes, yet governed by universal laws, a chaotic Syl's hidden order. This enigmatic hot Jupiter is not merely an object of study but a teacher, guiding humanity toward deeper understanding, not just of distant worlds but of our own place in the vast, unfolding. The on this planet serve remind not static entities. They evolve, interact, and reshape themselves over time, influenced by the forces that govern their existence. Through its dramatic atmospheric loss, this demonstrates the delicate interplay between a planet and its star, a relationship that defines the fate of many worlds, including our own. Its story also challenges us to consider the long-term destiny of planetary systems. The forces stripping its atmosphere today will one day affect other worlds, including those in our solar system. As the Sun ages and expands into a red giant, it will engulf Mercury, Venus, and possibly Earth. Could a distant observer, in some far-off system, one day witness our own world undergoing a transformation like this? If so, the insights gained now may help us understand and even prepare for the ultimate fate of Earth's planetary descendants. But beyond scientific insights, this exoplanet represents something more: the relentless human drive to explore, to push beyond the boundaries of knowledge, and to understand the worlds beyond our own. Its discovery in 1999 marked a turning point in exoplanetary science, helping to establish the methods that have since revealed thousands of distant worlds. It showed us that planets could exist in extreme conditions, that atmospheres could be studied across vast distances, and that each new discovery would only expand our sense of what is possible. In many ways, this hot Jupiter is a symbol of human curiosity and determination. Its study has led to technological advancements, inspired new research, and helped reshape our understanding of planetary diversity. It has set the stage for the next generation of exploration, from the James Webb Space Telescope to future missions seeking signs of habitability and even life beyond Earth. As we continue to study this distant giant, we are reminded of the beauty of exploration itself. A world with fiery winds and an evaporating atmosphere challenges us to think, experience, to confront the unknown, and to embrace the vastness of the cosmos. It forces us to ask deeper questions. How do planets like this evolve? What can they teach us about the origins of our own solar system? And what other marvels await discovery among the stars? Its story is not one with it is one that will evolve as our knowledge deepens, and our imagination expands. It stands as proof that science is not about reaching conclusions but about embracing the discovery, one as infinite as the universe itself. As humanity develops more advanced telescopes and exploration missions, the secrets of this fascinating world will continue to unfold. Its atmosphere, core, and dynamic interactions with its star will reveal new mysteries, each more profound than the last. And though we may never fully understand it in all its intricacies, its study will continue to inspire future generations of scientists, dreamers, and explorers. This is not just a distant object in the cosmos. It is a bridge between the known and the unknown, a testament to the power of curiosity and the thrill of exploration. It carries the story of a universe alive with possibilities, a universe that beckons us to explore, to imagine, and to dream. HD 209458b Osiris represents one of the most significant milestones in exoplanetary research. Orbiting a star in the Pegasus constellation approximately 150 light-years from Earth, this gas giant example of a hot Jupiter, a class of planets that orbit very close to their stars. Discovered in 1999, it was the first exoplanet confirmed through the transit method, where the planet passes in front of its star from our perspective, causing a temporary dip in brightness. This breakthrough not only secured its place in astronomical history but also marked a turning point in the study of distant worlds. Also known as a transiting exoplanet, HD 209458b is about 220 times more massive than Earth, with a radius approximately 1.4 times that of Jupiter. Despite its size, it orbits its star at an extremely close distance of just 0.045 astronomical units, AU, which is 1/8 the distance between Mercury and the Sun. This proximity results in extreme atmospheric heating, with temperatures soaring to around 1000 degrees Celsius 1800 degrees Fahrenheit, making it a classic hot Jupiter. One of the most remarkable aspects of this exoplanet is its atmosphere. It was the first where scientists directly detected atmospheric components using spectroscopic observations during transits. Sodium was the first element identified, offering an initial glimpse into its composition. Later studies revealed the presence of water vapor, methane, and carbon dioxide, making it the first exoplanet with a multi-component atmospheric analysis. Another crucial discovery related to HD 209458b was its atmospheric escape. Observations from the Hubble Space Telescope revealed that the intense radiation from its star is stripping away the outer layers. This process, known as hydrodynamic escape, has created an enormous cloud of hydrogen trailing the planet, resembling a comet's tail. Due to this phenomenon, it was dubbed an evaporating planet. The estimated escape rate is about 10,000 tons of hydrogen per second, a significant loss, yet not enough to deplete its mass within billions of years. The planet has also played a major role in understanding cloud formation in extreme environments. High-altitude hazes and potential cloud structures inferred from its spectrum suggest the presence of scattering particles in its upper atmosphere. These findings have provided valuable insights into the physics and chemistry of exoplanetary atmospheres, helping refine models for other distant worlds. Another fascinating aspect of HD 209458b is its orbit. With an incredibly short orbital period of just 3.5 days, its proximity to the star generates strong tidal forces, likely causing it to be tidally locked. This means one hemisphere is in perpetual daylight while the other remains in eternal darkness. The extreme temperature gradient between the two sides results in violent atmospheric dynamics, including supersonic winds that redistribute heat. Beyond its scientific contributions, this exoplanet has played a key role in advancing observational techniques. Its discovery pushed the limits of spectroscopy, transit photometry, and atmospheric modeling. Initially confirmed via the radial velocity method, which detects a star's wobble due to an orbiting planet's gravity. It was later studied using both radial velocity and transit methods. This dual approach allowed for unprecedented precision in determining its mass, radius, and density, setting a new standard for exoplanet research. HD 209458b has also provided crucial insights into planetary formation and migration. Theories suggest that hot Jupiters like this one did not form in their current orbits but migrated inward after forming farther from their stars. The exact mechanisms, whether interactions with a protoplanetary disk or gravitational influences from other planets, remain an active research. Studying this planet and similar ones helps refine planetary evolution. Another intriguing challenge posed by this exoplanet is its unexpectedly large size. Its radius exceeds based on standard planetary models, an issue known as the radius anomaly, which is common among hot Jupiters. Several explanations have been proposed, including additional just magnetic interaction and its star generate extra energy. Continued research on HD 258b provides valuable clues about these complex processes. Beyond its direct scientific impact, this planet has become a cultural and inspirational symbol in the search for extraterrestrial worlds. Its discovery and subsequent revelations about its atmosphere, orbit, and physical properties have captivated both scientists and the public. As a pioneering exoplanet, it represents how far humanity has come in exploring beyond our solar system. In conclusion, HD 209458b remains a landmark discovery in modern astronomy. Its detection marked the beginning of a new era in exoplanetary science, and its detailed study has provided essential knowledge about planetary atmospheres, migration, and evolution. As a hot Jupiter gradually losing its atmosphere to its star, it serves as a natural laboratory for studying extreme planetary environments. The legacy of this exoplanet lies not just in what it has taught us about a single world, but in how it has paved the way for the exploration of countless others across the galaxy. HD 209458b is one of the most well-documented and fascinating exoplanets ever discovered. Orbiting the star in the constellation Pegasus, giant is located approximately 150 light-years from Earth. 1999 was groundbreaking, as it became the first exoplanet transiting its host star. This key observation allowed scientists to study not only its orbit but also its physical and atmospheric characteristics in unprecedented detail, making it a cornerstone in the history of exoplanetary science. Often referred to as a pioneering hot Jupiter, HD 209458b has a mass roughly 220 times that of Earth, or about 0.7 times that of Jupiter. However, its radius is significantly larger, approximately 1.4 times that of Jupiter, classifying it as an inflated planet. This unexpectedly large size and low density challenge conventional models of planetary formation and structure. Researchers suspect that the intense stellar radiation from its host star and its close proximity may contribute, a trait observed in many hot Jupiters. The exoplanet follows an extremely tight orbit, circling its star at just 0.045 astronomical units (AU) and complete solution in 5 Earth. This close range exposes it to irradiation, heating its atmosphere to over 1,100 degrees. Heat causes the atmosphere to escape into space. Classification of an evaporating planet. From the Hubble have revealed hydrogen of oxygen trailing behind the planet like a comet's tail. This atmospheric escape insights into the evolution of planets. The atmospheric composition of this exoplanet has been a major focus of scientific research. First, where atmospheric components were directly detected, a precedent for the study of exoplanetary atmospheres. Early identified sodium revealed amongst include method. The detection of water vapor is significant, as it marked the first confirmed presence of water on a planet outside the solar system. This finding demonstrated the potential for detailed atmospheric analysis of exoplanets, even those located light years away. Beyond its chemistry, the planet's atmosphere in physical dynamics. Tidally one hemisphere daylight while the other remains in perpetual darkness. This sharp creates a dramatic tectonic wind speeds of up to 7,000 km (4,350 miles per hour). These winds redistribute heat in it, leading to turbulent and complex weather patterns. Observations have also suggested the presence of clouds and further complicating its atmosphere. The study of HD 2458b has provided crucial insights into planetary migration. Current models suggest that hot Jupiters like this one did not form but instead migrated inward after forming farther from their stars. The mechanisms responsible for with a protoplanet gravitational influences from other celestial bodies, area of the extreme exoplanet to which existing theories to propagations into the 4 planetary systems. Another enigmatic aspect of this world is its unexplained radius. Standard planetary models struggle to explain this, as its expectations-based temperature. Explanations include tidal heating, where gravitations would generate internal heat, or ohmic dissipation, a process field ionized gases in its converting kinetic thermal mechanism subject of ongoing research. This exoplanet has also played a key role in advancing astronomical techniques. Its discovery and subsequent combination of velocity method and transit photometry. The radial velocity method rotational wobble of a star caused by an orbiting, while the transit method measures the dip in as the in front of. To technique extensive details about the radius period and atmospheric property. This dual method approach has since become a standard in exoplanetary research, facilitating the discovery and analysis of distant worlds. Of HD 2458's unique characteristics. Its discovery and extensive study have paved the way for further exploration of exoplanets. The devils and example, the JAME telescope UST, build upon its legacy by offering even more detailed observations of exoplanetary atmospheres. Used to in of upcoming such as the Urian's aerial mission, which aims to examine the atmospheres of hundreds of exoplanets. In conclusion, HD 209b, often referred to as the roaster world, or the inflated gas sphere, landmark in the study of exoplanets. Its discovery of a new astronomy, while characterization has provided insights into planetary atmospheres, migration, and evolution. As one of the most exoplanets used to serve as a natural laboratory for exploring chemistry of extreme planetary environments. It has revealed about its own unique property, its role as a catalyst for the countless other worlds. H0945 used to be a cornerstone of science, inspiring new generations of research into planetary systems beyond our own. Its atmospheric properties, orbital mechanics, and contributions to advancing observational techniques provide a near-endless array of study opportunities. Scientists have used this exoplanet as a proving ground for refining methods that characterize distant worlds, not only in terms of their fundamental parameters but also their complex behaviors and interactions with their host stars. One of the most remarkable aspects of this boiling exoplanet is its evaporating atmosphere. The hydrodynamic escape of hydrogen, oxygen, and carbon detected from the planet provided the first direct evidence of large-scale atmospheric loss on an exoplanet. This phenomenon has significant implications for understanding the long-term evolution of planetary atmospheres, particularly for those in close proximity to their stars. Atmospheric escape can strip smaller planets of their gaseous envelopes entirely, potentially leaving behind barren rocky worlds. Studying this extreme case allows scientists to model the process under the most intense conditions, offering valuable insights applicable to a broad range of planetary systems. Beyond atmosphere, this exoplanet is a fascinating case study for tidal locking dynamics. Likely locked in a synchronous orbit, one hemisphere remains in constant daylight while the other is permanently shrouded in darkness. This configuration results in extreme thermal contrasts, with the day side reaching blistering temperatures, while the night side remains significantly cooler. The redistribution of heat between these two hemispheres is facilitated by supersonic winds, driven by intense stellar radiation. These high-speed currents transport energy across the planet, influencing its overall atmospheric structure and circulation. By examining these interactions, researchers gain valuable insights into atmospheric behavior under extreme tidal locking conditions, which is also relevant to rocky exoplanets' inhabitable zones. The inflated side 209458b remains another puzzle. Its radius exceeds theoretical predictions for a planet of its mass, leading to ongoing debates about the mechanisms responsible for this anomaly. Tidal heating, caused by gravitational interactions with its star, may generate sufficient internal heat to expand its gaseous envelope. Another possible explanation is ohmic dissipation, where interactions between the planet's magnetic field and ionized atmospheric particles produce additional heating. Processes, while still theoretical, highlight the complexity of planetary physics and the need for continued observations to refine our understanding. This exoplanet has also significantly advanced our knowledge of atmospheric chemistry. The detection of sodium, water vapor, methane, and carbon dioxide in its atmosphere marked a turning point in exoplanet research. These discoveries, made possible through spectroscopy, have allowed scientists to analyze the starlight passing through the planet's atmosphere during transits. By studying absorption features in the spectrum, researchers can identify specific molecules and estimate their abundances. This breakthrough not only provided a clearer picture of HD 209458b's atmospheric composition but also laid the groundwork for studying atmospheres on smaller and potentially habitable exoplanets. Another key contribution of this planet is its role in understanding planet-star interactions. Intense radiation and stellar winds from its host star play a crucial role in driving atmospheric escape. These forces also influence its magnetosphere, which helps shield the planet from high-energy particles. Examining its magnetic environment provides valuable insights into how planets in extreme conditions protect themselves from stellar radiation. Such studies have broader implications for assessing the habitability of planets orbiting active or young stars. HD 209458b has also deepened our understanding of planetary migration. Hot Jupiters like this one are believed to form much farther from their stars in colder regions before migrating inward. The exact mechanism behind this movement, whether through interactions with a protoplanetary disk, gravitational perturbations from other celestial bodies, or a combination of factors, remains a topic of active research. The orbital properties of this gas giant, combined with its atmospheric and physical characteristics, provide critical data for refining these theories. Additionally, the presence of high-altitude hazes and clouds in its atmosphere has enhanced our understanding of aerosols in exoplanetary environments. These hazes scatter light and obscure certain spectral features, complicating the detection of atmospheric molecules. By studying the scattering effects in its spectrum, scientists have been able to develop models that improve the accuracy of atmospheric retrievals for other exoplanets. This research is crucial for upcoming missions aiming to characterize the atmospheres of Earth-like planets, where clouds and hazes may similarly impact observations. This giant close-in planet also serves as a natural laboratory for studying the effects of extreme stellar irradiation. The intense heat it experiences profoundly impacts its atmospheric chemistry, potentially triggering photochemical reactions that produce exotic molecules. These processes are of great interest to researchers studying planetary chemistry across a range of conditions, including those found on temperate worlds. Finally, the cultural and scientific legacy of HD 209458b cannot be overstated. As the first transiting exoplanet ever discovered, it has inspired countless researchers and played a pivotal role in shaping modern exoplanetary science. Its detection marked the dawn of an era where detailed characterization of distant planets became possible. The techniques refined through its study have since been applied to thousands of other exoplanets, broadening our understanding of the diverse planetary systems within our galaxy. In summary, HD 209458b, often referred to as the boiling gas giant, the evaporating planet, or the roaster world, remains a fundamental target in exoplanetary research. Its unique characteristics, from atmospheric escape to extreme weather patterns and inflated size, have provided unparalleled insights into planetary physics, chemistry, and evolution. As a trailblazing exoplanet, it continues to drive new discoveries and innovations, cementing its legacy as a key stepping stone in our quest to understand the cosmos. HD 209458b, known by many names, Osiris, the evaporating planet, or the inflated giant, is far more than a scientific curiosity. It stands as a beacon, illuminating the vast, complex, and untamed world of exoplanets. While much of its physical nature has been extensively studied, lingering mysteries and tantalizing possibilities continue to intrigue scientists. The deeper we probe into its secrets, the more it reshapes our understanding of planetary science, reminding us of how much more remains to be uncovered. One of the most fascinating aspects of this exoplanet is its role as the prototype for studying atmosphere.